Hello, everybody, and welcome to today's webinar presentation, Builds Stateful Workloads in Kubernetes, brought to you by MemSQL. I would like to introduce to you our presenter. Rob Richardson is a software craftsman building web properties and ASP.NET, EndNode, React, and Vue. He's a Microsoft MVP, published author, and frequent speaker at conferences, user groups, and community events, and a diligent teacher and student of high-quality software development. You can find this and other talks on robrich.org/presentation and follow him on Twitter at @rob_rich.
Hi, everybody. I'm Rob Richardson. Thanks for joining us. I'm really glad that you're here, and I'm grateful that we get to talk about building stateful workloads in Kubernetes. Here's the part where I tell you I'm definitely going to post my slides on my site tonight. You're going to email me tonight. Tomorrow, you won't see them. In a week, in a month, in about 3 months, you'll get tired of waiting for me to post my slides on my site. You'll email me. I'll definitely reply promptly in 6 months and say, no, I'm definitely going to post them on my site tonight. And I'll never post them at all, which is why you can go to my site right now. You can go to robrich.org, click on presentations here right at the top, and here's building stateful workloads in Kubernetes. You can click on here to get to the slides that we're going to look at right now. They are online right now. Head over to robrich.org and click on presentations. While you're there on robrich.org, let's click on About Me and see some of the things that I've done recently. I'm a technical evangelist for MemSQL. I'm also a Microsoft MVP and a friend of Redgate. AZ GiveCamp is wonderful. AZ GiveCamp brings volunteer developers together with charities who otherwise couldn't afford software services. We start building software for them Friday after work. Sunday afternoon, we deliver that completed software back to the charities. It's a really, really fun thing to do. And if you're ever in Phoenix, come join us for the next AZ GiveCamp. Or if you'd like to see a GiveCamp in your city, contact me and let's see if we can install that in your community as well. Some of the other things that I've done, one of the things I'm particularly proud of is that I replied to a .NET Rocks podcast episode. They read my comment on the air and they sent me a mug. Woohoo! So that's my claim to fame, is my .NET Rocks mug. So let's talk some more about Kubernetes. We talked about this guy, Kubernetes. Kubernetes was definitely designed to be a stateless platform. And so when we first look at Kubernetes, we probably build something like this. We've got our containers running inside of pods. We have a service in front of it. We may have an ingress controller that routes traffic to it. We got this. This is easy. Well, yeah, it takes a little bit to get to this point, but this is really great. Users can come hit our ingress controller. They can route to the service. The service goes to the pods, and all of that works great. However, our apps probably look something like this instead. We have a little bit more complexity here. So we still have our containers and they're running inside of pods. We still have our service routing, round robining between them. But with our ingress, we're probably terminating SSL here. So we'll have a certificate. We'll have domain configuration that is probably different between environments. Additionally, we'll likely have database content or maybe file storage content. And we need to store configuration details to get to that content. And so we have a whole lot of state in our application that we didn't have in kind of that simplistic method, simplistic state. So how do we get this state inside of Kubernetes? That's what we'll dig into today. Today's the day 2 experience where we talk about getting state into Kubernetes. So what is state? Well, here's some states. This plays a whole lot better in front of a live audience where I can hear the laughs, but hopefully you're laughing with me and not at me. Here's some states, but those aren't the states that we're going to talk about today. Here's the states that we're going to talk about today. State is anything that lives beyond the current lifetime. And so we can think of state as things living beyond the function call. That's likely what we do when we're writing software, is building variables that may live longer than a function call. As we talk about web requests, we may talk about things that live longer than a request and response cycle. So as I go save the data, I then need to go run another request to get that data back. And so that's the state that I need to save. We also have state that talks about server restarts. So I may need to save files on the file system. And if the server restarts, I want those files to stay on that file system. Or perhaps I'm going across a load balancer, and so I need that file system to be shared across all my web servers, that state as well. So these are the types of things that we're going to talk about today, is getting that state stored inside of Kubernetes. We talk in general about these types of mechanisms: configuration details, secrets, data stores, file stores. And we may also talk about singleton services, services where it's making business decisions and it needs a holistic and complete view of all of the system. So we need to have that one just maintain all of the pieces. So singleton services. A database is a great example of a singleton service. We can't have more than one copy of the database in our environment. We may have different machines part of a single cluster, but ultimately we need to have that one unique database. It's not like each pod can connect to its own database and store its own data, and then a different pod may get to a different database. We need to have that one single source of truth. So we talked about configuration, secrets, data stores, and file stores, and these singleton services. Let's dig into each one and start to explore how those work inside Kubernetes. Now, one of the big annoying things is when we say CubeCTL Get All, we don't actually get everything. As its name suggests, it's supposed to get everything, but it really doesn't. What it gets is all of the stateless resources. And it made this choice very specifically because for things that can't be recreated easily, they don't want to expose them prematurely, so that, you know, if we were to delete and recreate everything, maybe we couldn't get that secret back because we didn't have the unencrypted data. Or if we destroyed and recreated a stateful service like a database, we couldn't get that data back. So CubeCTL Get All very specifically doesn't show stateful resources. The bummer part then is as we go start exploring these stateful resources, we'll probably need a different mechanism for getting the things. Now we can definitely say CubeCTL Get and each of the things and just list them. But if we say CubeCTL Get All, we also need to know that maybe our resources aren't there. So there is a mechanism to get all the things. It's massively complex. I go grab all of the resources, CubeCTL API resources. That will list all of the resources in my cluster, including custom resources, perhaps added by third-party packages. Given that list, I could run that through an awk script to go grab the name, and I could comma separate them, and then I could say CubeCTL Get that big list. So that CubeCTL Get CubeCTL API resources, pipe it to awk, pipe it to grep, pipe it to zargs, pipe it to sed. I have that as an alias in my shell so that I can get all the things, including all of the stateful resources. You may choose to grab these slides from robrich.org and copy that into your bash profile as well, and have a similar alias for getting all of the things. The bummer part is this has been raised a couple of times of, you know, why doesn't CubeCTL Get All really get all? Or can we create another get that gets all the things? You know, get all -f or something? And yeah, no, they're not going to do it. Okay, so hitting that point again, CubeCTL Get All won't actually display all. That's okay. Awesome. Well, then let's dig into volumes. Here's our first stop in those suite of stateful resources. Volumes. So with a volume, we probably want to store these files beyond a pod restart, or to share files between pods. Now, the cool part is this is not that unlike a network share, where we just have a drive off in the on the network where we can store things. And so that's kind of a good analog, but we're actually going to create a symbolic link into the pod. So a certain directory just happens to be stored elsewhere. Now, because it's a network share, file locks don't work the way we expect. So if I lock a file in one pod and then try to read it or write it in the other pod, that operation will work just fine. So we need to architect our app slightly differently to not assume that files are locked. Perhaps each pod uses a different folder, or perhaps we are only doing unique file names based on operations, but we need to be careful there because file locks don't work the way we expect. So here's a YAML file that defines a pod referencing a volume. And so I've eliminated some of the normal things that we would see in a pod file, all of the pieces about resiliency and health checks. But we've defined an image, we've defined a name for our container, and then we have this volume mount section. And this volume mount section talks about the details of the volume. So here we give a name, the volume, and then the mount path, this is the path inside the container. So in this path in container to dir, if my app opens a file inside that directory, it's as if it's any other file running inside this container. It's just a file on the file system. I can add more folders inside this directory. I can add more files to this. I can read and write those files. And to the application, it just believes that it's part of the disk. But this volume here is defined here, the volume, and I can specify various mechanisms for getting that volume to be more durable. So in this case, I chose to make it a host path. And so here's that path to the directory on the host. I could choose to put this inside my NAS or on a network share or in an S3 blob or wherever it makes sense to hold this data. I can make that much more durable. Now this is interesting, and this is a great example of getting file storage off of my pod into a more durable place, but it kind of mixes things. So the magic question is, well, who owns that storage spot? Should a developer, as they're crafting the rest of that YAML file and identifying the version of the image it should use, should they own that hard drive? Or operations really wants to ensure that that's backed up correctly, so they want to identify the correct location and perhaps naming convention inside the SAN. And so we really want this separation between developer and operations. And that's where we can get into a really cool abstraction in Kubernetes, where we can talk about persistent volumes and persistent volume claims. Now this does get a little bit hairy, so I've kind of nicely drawn it so that we can follow it. We have a storage, a hard drive, and we can carve that storage up into blocks. We'll call these blocks persistent volumes. Each block represents one thing that a pod can check out. So we'll have a persistent volume, and then we'll have a persistent volume claim that claims one of them. So a pod can say, I need a hard drive, and I need it to be 5 gigs, and so it'll go find a 5 gig spot, and it'll pull it out, and it will symlink that as a folder within the container. We have storage, we have the persistent volume, we have the persistent volume claim, and we have the pod definition. Now the cool thing is the persistent volume claim and the pod can be owned by the developer. The persistent volume and the storage can be owned by operations. And so we can have this really cool, clean separation of concerns here, where we can ensure that that storage is backed up correctly and that it's allocated according to our provisioning needs. And the developer can also assume that they just need storage and it just magically works, connecting it to the right folder within their pod. And so that's a really elegant way to have persistent volumes and persistent volume claims that can separate that dev and ops point of responsibility. So creating a persistent volume, here's that ops part of it. We specify that host path, that path to where we want to actually store the directory. We can specify access modes, read write once in this case. We can also say read write many or read only. And then we give it a storage. In this case, I said this path has a storage of 10 gigs. If you go over 10 gigs, then that drive is full. Now I may have more space on my hard drive. I just carve it into 10 gig pieces. Here's that persistent volume, and to claim it, the developer will create a persistent volume claim specifying the details that they need. So in this case, I said I need something that is read write once, and I need it to be at least 3 gigs. Now the cool part is we specified this as 10 gigs. I said I want 3 gigs or more, and so it says, okay, I'll grab that one. We don't need any other details other than the read write once match and the storage amount. We can specify other details like availability zone affinity or storage speeds, quality of service details, but those are the two that we definitely need to do: read write once and the storage. So with that persistent volume claim, now here in my pod definition, rather than specifying where it's actually stored, I'm going to reference that persistent volume claim's name. So the pod will reference the persistent volume claim, and all the rest of it will work. Here in the volume mounts, I'm specifying the path in the container that I want it to connect to, and everything just works. So we have the storage, we have that persistent volume. A pod can claim one of those persistent volume blocks and attach it into its container, and now we have persistent storage inside of our pod. And we have that nice separation between dev and ops. So that's persistent volumes, and now we have file storage. We can upload profile pictures. We can save CSV files that we have uploaded. All of the content associated with files we can now stick into our application. But how do we know where that location is? Perhaps we want other config details, or maybe we want config details that are environment specific. Now, the cool part about configuration within Kubernetes is we can mount these either as files on disk or as environment variables, and we'll see examples of each. In Kubernetes, here's our simplistic example where we just list the environment variables that we want to define here in our pod. Here's the environment variable, here's the value we want it to be set at, and so then in our application specific way, we can read that environment variable and take action. Now, similar mechanism, who owns this configuration data? Does the developer have to know all of the details in each environment? What if operations really wants production secrets that are not exposed to developers? And so let's look at a mechanism in Kubernetes where we can split that out as well. We have a config map. And a config map identifies all of those details. So for example, here in this config map, I have some data. I have a database, MemSQL, logging is set to true, my API URL is set to this URL, and these can be environment-specific details stored by operations. As a developer, I then just reference that config map by name, and it just works. Here, instead of environment variables, I'm saying env from config map ref, and I just list that config map name. So as a developer, I can have one pod definition that will work in all environments. My application and my container can work identically through all environments. And then we just have environment-specific config maps that happen to be preloaded into our cluster so that we can reference the correct database. All those database connection details just get pulled right in, and we're able to connect to our database just fine. So we can also mount this config map as files instead of as environment variables. And we may choose to do this so that it's not available all the time, maybe a little bit less discoverable. So here we specify the mount path. That's just some path in the container where I want to store all of my configuration details. Inside that folder, there will be a file for each of the config map keys. So inside the path and container to dir, I would have a database file, and I would have a username file, and I would have an API URL file, and my application could open that file, read the secret, and take appropriate action. So some of these configuration details we may want to keep in secret. Rather than specifying them globally and storing them in plain text, we may want to use these encrypted. So let's dig into secrets. With secrets, this is stored encrypted at rest since Kubernetes 1.13. Arguably, that's kind of late. Before this, it was stored as base 64 encoded. Oops. And because the secrets needed to be available on all hosts, because all hosts may run any pod, then if I compromise one of the hosts in my cluster, I could get access to all the secrets, just base 64 decode them and get at them. That was solved in Kubernetes 1.13, and so now Kubernetes secrets are stored encrypted at rest. They are available on every host, so we do need to protect the hosts to ensure that those secrets are preserved, but they are encrypted at rest now. Alternatively, I may choose to put my secrets in a key vault like HashiCorp, and that's a great solution as well. So if I create these secrets, I can do that in a YAML file like I do here. This YAML file specifies the secret name is DB connection, and then here's my list of secrets that I would like in this secret container. My database username is dev user, my database password is password, and I can store these in string data just in plain text. If I flip this string data with data, then these will be base 64 encoded, and so base 64 encoding things is a smidge weird. They're still not secret, but here's that YAML definition. Now I recommend not using this YAML definition because it's really easy to accidentally check this into source control. And once I've checked this into source control, then I've lost that secret data. I need to rotate my keys, I need to change my passwords. That data is now exposed. So rather than using a YAML file, I recommend using CubeCTL to create secrets. Now here, this is one long line. Each of these backticks represents a continuation of that line. Here, as I'm creating the secret, I'm specifying the literal content for each thing. I can do this in a shell where I can shortly thereafter kill my history, or I can pull that in from a file so that I don't even expose my passwords to the command line. But I can pull in those either as base 64 encoded content, or in this case, because I said from literal, I can pull that in from just plain text data. So I say here in my DB connection piece, I have two pieces of data I'd like to store in the secret. One is named username and its value is dev user, and one is named password and its value is password. So we usually don't change secrets a whole lot within our cluster. We just need them to be present. And so I find this command line or an API call to be a whole lot easier to maintain and to keep secure rather than a YAML definition. So now as I pull them into my application, we can do a similar kind of abstraction. Ops will own creating those secrets, perhaps rotating those secrets, and developers can then mount those either as environment variables or as files. In this case, I'm choosing to mount it as a file, so I have a volume mounts. Here's my mount path, that's the folder inside the container. I'm mounting it as read-only as true because I really don't want to change those secrets. Not that I can, but I'm just making that explicit here. And then in my volume definition, previously we identified it from a config map and now are from a persistent volume claim. And here, instead of a persistent volume claim, we're referencing it as a secret. So I have my secret name, DB connection. And because I've specified that secret name, then in this directory, I'll have two files, a username file and a password file. Whenever my application needs to connect to the database, it can read those two files, grab those secrets, and continue on. I can also choose to mount these as environment variables. Down here at the bottom, I'm still referencing that secret key ref as DB connection, but I can also specify the key. In this case, that is password, and it's going to set an environment variable called DB password. Same thing with DB username. I'll set that value from the secret, and that'll set that environment variable within my container. Now I can have one pod definition that is universal across all environments, and it can just assume that those secrets exist and pull in the applicable data as it starts up the pod. So we've done some really, really cool things. We've got configuration details here, and we've got secrets so that we can store secret data. We can separate those details between developers and operations to ensure that that content is preserved across environments, and secrets don't need to leak into hands that don't need them. We've got volumes where we can store persistent data, and that may be enough with volumes and config maps and secrets to be able to get the majority of your application into Kubernetes. But let's dig into stateful sets and kind of level up and see if we can get even more of our application into place. Stateful sets allow us to create mechanisms where we have machines that need to talk to each other and have predictable names, perhaps hosting a cluster like a database cluster. So this is a bundle of machines. It creates pods with predictable names, and with that we can then communicate between containers. It's easy if I'm creating a cluster of machines, or if I'm trying to connect to a cluster of machines where I have to list the machines, and now, if the pods are coming and going and each one gets a random name every time, now does my application need to keep track of those and go ask the system how to connect to? We avoid all of that by creating a stateful set. We can create a stateful set that will have a known number of machines, and each machine will have a known name. And if one of those machines goes down, then a new machine will come back with that exact same name. And now we don't need to keep track of that list of machines. We can think of a stateful set as a deployment with predictable names. A deployment is that mechanism where I can say, I would like 3 copies of it. And so it'll always ensure that 3 pods are running. In this case, this stateful set is that deployment with 3 pods running, but we know what those machine names will be. They'll be 0, 1, and 2. It'll ensure that 2 doesn't start up until 1 is running as well. So stateful set use cases. We might want to spin up a Kafka cluster, or an Elk Stack cluster, or a database cluster such as MemSQL. MemSQL uses lots of machines to distribute our data across commodity hardware so that we don't need one big beefy machine to be able to store our database. And with that distributed nature of MemSQL, we do need to have lots of machines, and they need to be able to coordinate together. So with a stateful set, we can put our MemSQL machines into our Kubernetes cluster and ensure all of them are playing well together. So here's that mechanism of a stateful set. We have each pod with a predictable name. So here's pod-0, here's pod-1, here's pod-2. Each one will have a container running in it. And then we have this headless service that allows for communication between pods. If a container wants to reach out to a particular pod, it can through this headless service, given its known name. And then outbound or inbound traffic can reach in through this headless service, or we could create another service that is specific for communicating to some or all of these stateful set containers. So here's a YAML file that defines that stateful set. You'll notice it looks not that unlike a template deployment definition. We have the number of replicas. We have a template that describes how we build our thing. We'll give it a service name. That's that headless service that we must create. Our match labels, all of this kind of mirrors a deployment. But in this case, as we specify our template matches the same mechanism as well. The only real difference is that we've identified it as a stateful set, and we're listing our headless service that we're using as well. So here's that headless service, and what makes it headless is this cluster IP of none. The cluster IP of none says it's not going to create a cluster IP. I can only connect to it by name. And the cool part then is that I can, if I'm connecting to it to connect to any of the machines, I can do it much like I would a normal service. Let me just curl that service name. But if I want to speak to a particular machine, then I can talk to that machine. So in this case, perhaps the DB0 needs to talk to the DB1. So it'll just connect to the DB1.db service, and now it can communicate directly with that second pod through this headless service. Most apps will connect to it this way, just as DB service, and at that point, it'll just round robin across all of them. So as I have my MemSQL database set up, I'll create this headless service to connect to my aggregator nodes and just call that the aggregator service. But then as the aggregators need to connect to each other, or as the aggregators need to connect to the leaf nodes, then they can do that by referencing them by name here. So here's that stateful Kubernetes service. Now, in our application, we had a whole lot more pieces. We had a certificate that has and a domain name. We have connection details off to a database cluster. We have paths to our file storage. We have storage details, things that need to stay more persistent. And as we look through each of these pieces, we can see that not only do we have all of our normal stateless services, our containers, our pods, our services, but we also have all of the stateful pieces. Here's a config map that specifies the domain name. Here is a secret that is the certificate. Here's a config map or a secret that specifies the connection details to get to our database cluster. We have persistent volumes and persistent volume claims that allow us to get to durable storage elsewhere. And we have a stateful set that allows us to define a database cluster or another cluster that takes multiple machines of known machine names. All of these pieces, these stateful pieces, now allow us to move the rest of our application into our Kubernetes cluster and maintain business continuity across the complexities that become our application. Volumes, secrets, config maps, and stateful sets are that next level that get us to the day 2 experience in Kubernetes. MemSQL created this webinar and sponsored it, and I'm really grateful for them. If you'd like to learn more about MemSQL, go to memsql.com/download, or you can reach out to them by email at team@memsql.com. As you grab these slides from robrich.org, you can definitely click on these links to be able to get started with MemSQL Helios or to reach us by Twitter or email. I'm really glad for MemSQL for sponsoring this webinar, and it's been really great to be able to share this with you. Are there any questions?
Awesome. So with that, we will move on to this Q&A portion of the webinar. Thanks so much for everything, Rob. So your first question is, how do I version my container secrets?
Good call. How do I version my container secrets? We looked at a YAML definition that defined those secrets, and I talked about how it's scary to check those in the source control. Perhaps we want to create a separate repository that is known to be private and check in those YAML files into the separate repository that keeps it secret. That's one way to version our secrets. Another way is to keep them in, keep the versions elsewhere, perhaps in a vault like HashiCorp Vault or Azure Key Vault, and that will allow you to version the secrets as well.
Awesome. Okay, so your second question is, how do I get HTTPS certificates into the web server containers?
Good call. How do I get them into the web server containers? Let's come look at this stateful Kubernetes diagram and look kind of at how we did that. Now, if we were to terminate HTTPS here at the pods, we could map in a secret or a config map to get that content in here. I would really recommend a secret because it is a certificate. And so I could just map that in as one of the secrets exposed either as an environment variable or as a file. In this case, the certificate may get big because it is it's a decent size, so perhaps as a file might make more sense. But I would argue, as we step back, probably we don't want to terminate SSL here at the container. Probably we want to terminate SSL at the firewall, at the gateway up here. And the cool part then is I don't need to get the certificate into my container. I can get my certificate here into my ingress controller, and I have a single config map or a single secret that points it to the ingress controller, and the ingress controller can terminate SSL. At that point, all of the traffic downstream is just HTTP between pods, and that might be an easier way to solve that problem. If I do need certificates in this communication between ingress and service, between service and pods, then that's where I would reach for something like Istio or Linkerd, a service mesh. And that service mesh can ensure that all of the communication within the cluster is encrypted separately. I still terminate SSL at the ingress controller, the public SSL, but then Istio picks up and will encrypt traffic between ingress to the service and between service to the pods using sidecar proxies. That was a great question.
Thanks so much for answering that one, Rob. So your next question is, why would I choose containers over virtual machines like EC2?
Good question. Why would I choose containers over virtual machines? You know, you're telling me that this thing is simple now. You know, we've got all these pieces, but there's a lot of complexity to this diagram. You know, really all I wanted to do was do this part, and now I have to do this part and this part. Yeah, there is some complexity to containers, but what makes containers really, really powerful is that they are ephemeral isomorphic hardware. We can spin one up at the drop of a hat, and it only contains the differences between what I need to run my application and the host machine that is running that container. So containers end up being a lot lighter weight, a lot smaller, where a virtual machine may be, you know, tens or hundreds of gigs. A container is usually tens or hundreds of megs. And that shrink in storage costs also translates into runtime efficiency as well. I can get a whole lot more containers running in my cluster than virtual machines. It does mean that I need to think more about how I deploy my application. I need to split it into pieces. I do need to define my services that will load balance across my containers. I need to terminate my SSL at ingress perhaps, or create other abstractions to be able to handle these containers. But it is a whole lot lighter weight mechanism to run. And because it's much lighter weight, then you'll get operational efficiencies just straight out of the gate. Ultimately, if you can move your application into containers, you will probably make it faster and easier to run straight away.
Awesome. That was such a great answer, Rob. Thank you.
Yeah, definitely. That was a great question. Thanks for the person who asked it.
Yeah, of course. It really was a great question. Your next question is, how do I do a deployment or a stateful set with one pod on each node in the cluster?
Oh, good call. So I want to create a stateful set, much like I would create this stateful set for a database cluster. But instead of having a known number of pods, I want to have one on each machine in my cluster. Maybe I want to do like monitoring or shipping logs into Prometheus or something like that. That is called a daemon set rather than a stateful set. And we can think of it exactly like a deployment. A daemon set is a deployment with one node, with one pod on each machine in the cluster. So ultimately, I'm not specifying the number of replicas. I'm just specifying, hey, go do it. And it'll put one pod on each node in my cluster.
Perfect. We have another question for you. How do I get MemSQL running on Kubernetes?
That is a great question. We talked about how to create stateful sets and how to get MemSQL built that way. MemSQL has 3 different types of machines. We have the leaf nodes that actually store the data. We have aggregators where clients connect to that, and that will push the data across into all the leaf nodes that need to participate in that. And then we have a master aggregator whose job it is to control the health of the cluster. So ultimately, as we get MemSQL into Kubernetes, we'll probably need 3 different stateful sets. One for all of the leaf nodes, one for the aggregator nodes, and one for the master aggregator. The cool thing is you don't need to build up that complexity. If you want to, you can use the Kubernetes operator created by MemSQL. And the cool part is that creates a custom resource definition where I can specify here's how many aggregator nodes I want, here's how many leaf nodes I want, and the operator will take care of deploying all of the pods, keeping them running, deploying all the stateful sets to ensure that I have durability and availability. I can also specify across availability zones if I would like. And ultimately, that operator then hides all of that complexity from us, removes all of the need for that complexity. So I can just deploy the operator and fire it up, and it just works. If you want to take it to the next level of using Kubernetes and avoid all of that complexity, then Helios is actually running on top of the Kubernetes operator. It is exactly that same database engine. And so with MemSQL Helios, you just sign up, you provision an on-demand database, and it'll give you a database connection. At that point, enter those database connection details in your application, and you have database on demand. The really cool thing is that all of the database backup and always on details and all of that border security pieces that you might have to run by yourself is managed completely by MemSQL Helios. MemSQL Helios is available in Google Cloud and in Amazon, and coming soon in Azure as well. And so you can deploy Helios, you can start up a Helios cluster in the region of your public cloud that you would like. If you'd like to grab MemSQL Helios, memsql.com/download will definitely get you there. And MemSQL Helios is a really great product for having a always on database as a service. It's a great solution.
Awesome. Thanks for elaborating on that, Rob. Your audience seems to really love the topic of this webinar. There's a few more questions for you until we close out for the end of the day. So with that, who should own the Kubernetes YAML files, developers or operations?
That is a good question. Who should own the YAML files? When we're digging into, pardon me for making you dizzy for a moment, when we're digging into volumes and persistent volumes, we started talking about this mechanism. If developers choose to own these, then developers should own the persistent volume claim and the pod definition, probably also the service and the deployment. And operations should own the persistent volume and the storage. That's a really elegant separation concern where all of the physical details are owned by operations and all of the application-specific details are owned by developers. Now, we may choose to take a little bit different approach as well. We may just say developers just want to focus on their app and they just want to deploy it to somewhere, at which point we could opt to make all of the YAML files an operation-specific thing. Perhaps they're just bundled in as part of the build, and developers just build their application and commit it, and the source control or the build server, the DevOps pipeline, actually pulls in all of the YAML files and containerizes the application and does all the things. That is a way to kind of simplify those details away from developers so they don't have to worry about it. The downside is it makes it more difficult for developers to really experience the same mechanism that applications will run in production. At that point, developers say, well, how do I SSH into my container to do the last little bit of configuration? That's not really a thing in containers. So if you can give the YAML files to developers, I think that will really help in leveling up their skills and helping them really experience the system as it runs in production. If developers really, really don't want to deal with it, perhaps you have a separate DevOps team that handles the integration pieces that would kick off during the build. But that does create layers of hierarchy that can get in the way sometimes.
Awesome. Hey, Rob, speaking of containers, why would I use containers over a platform as a service like Azure, Web Apps, or AWS Elastic Beanstalk?
Yeah, that's a great question. Similarly to when we're looking at here about, why wouldn't I just do these on virtual machines? Why wouldn't I just hand them to a platform as a service? Elastic Beanstalk is great for hosting apps. I may want to, put them even into Lambda as function as a service. And that is a great abstraction platform. Under the hood, they probably have this load balancer that goes across all of the instances. They may have an ingress mechanism where I'm specifying the certificate. And if their assumptions on my hardware really work for me, then Elastic Beanstalk or Azure Web Apps may be perfect. As I get deeper into microservices, and I really want to take control over all of these containers and pods, and I want to create a mechanism where some containers are exposed publicly and some are only exposed to other services. As I want to get into authentication between services, then that's where the platform as a service mechanisms kind of fall down. They're built more for that simpler case where I have arguably a monolith website that I just want to get online. As I want to dig in deeper, I may want to take control of those pieces, and that's when I want to go more towards containers and Kubernetes. If I'm just in that simpler case, maybe platform as a service or function as a service might even be a cheaper option for me.
Awesome. So it looks like we have time for one more question. Let's see here. Okay. Should I provision my volume storage in the Kubernetes worker nodes hard drives?
Good question. As we were doing the volumes here, we were looking at, this one was mounted to host path, which means written onto the hard drive of the Kubernetes node, that Kubernetes machine. And that is dangerous. We're assuming that that node stays, that that's persistent. I probably want to put this on my SAN or put this in an S3 bucket, perhaps an Azure Files storage, where that data is more durable and available across all the nodes in the environment. If I just need a temporary file, a temporary folder to be able to dump stuff for a time and make sure that it's available for the next request, perhaps host path is sufficient. But it depends on the need. Host path is definitely faster, and so we won't have network latency associated with getting to that persistent store. But it is fragile. We're assuming when we say host path that we don't have pods on different nodes in our cluster, and that we don't have, and that our host stays up. If that EC2 instance that happens to be running our cluster reboots or dies, then that host path resource may be gone on next request. Host path is great for temporary things. It's not great for super durable things. Really fun sharing questions with you. I'm glad that you had such engaging and interesting questions. As you find more questions later, reach out to me on Twitter at rob_rich, and you can definitely grab these slides right now on robrich.org. Thank you again to MemSQL for hosting this webinar. This was really, really fun to get to share Kubernetes stateful resources with you.
Awesome. Yeah. And like you just said, Rob, thanks so much for answering all of the questions that the audience had for you today. And with that, I would like to thank Rob for his great presentation. It was super engaging and we loved it. I would also like to thank MemSQL for providing the audience with a great webinar. Lastly, thank you to everyone who attended today, and we hope you learned something new that will help you with your developer career. Have a great day, everyone.
Thanks, everyone.